Okay, so any questions firstly about last time? Stuff that I talked about, or was it a bit too cultural specific? Last time I tried to structure this in the through this so-called, what I call the ladder of dualities. So the first rung were these T-dualities, and mirror symmetry was the sort of more sophisticated version of this, and this is what I talked about last time. And it's historically also the oldest, something from maybe 85 to 90, and were the initial discoveries. And then we had two more rungs in this ladder. And finally, gauge string or open-close string dualities. So we talked about this. And what was this? This was the statement that the generating function of a particular physically relevant quantity, the amplitude, the string amplitude, is also in the context of topological strings. It is interesting enumerative geometric object. So this Fg of T, the T's were these complexified scalar parameters, and this was the generating function, which had an expansion like this. I just saw on the board that there was a lecture on the moduli space of stable maps and so on. So this is basically, these ng betas were basically those integrals of some Euler characteristics on that moduli space. So this is computed by the topological A model on, let's say, a Calabi-Yau threefold M, and these give you this gives you the generating function of those quantities. So this is the right-hand side is something hopefully mathematically you are comfortable with. The claim is that the left this generating function can be computed by a physically relevant object, this topological A model, and the non-trivial statement about the mirror symmetry was that you can compute this. So the reason there's a duality is that it turns out that this object, which is, if you try to do it straightforwardly, is not very easy to compute. You can do it by using the fact that the corresponding physical object we know from physical arguments or sort of the semi-mathematical arguments, that it's computed, it can be computed equivalently by a different, apparently different quantity, a topological B model on a different object on a Calabi-Yau 3, which is the mirror Calabi-Yau. I didn't really tell you how one finds the mirror or anything. I just told you that the mirror is, there is a mirror Calabi-Yau, which has its H11 and H21, the non-trivial Betti numbers, Dolbeault cohomologies interchanged with that of M. And here you can compute a similar quantity in the B model on this Calabi-Yau. And this quantity is, as I said, classical, because it's computed by some computations of some period integrals in the geometry, and in many cases can be done explicitly. And this tau, combined with a knowledge of the so-called mirror map, which tells you the dictionary between the complex structure parameters. So these are complex structure parameters of the mirror, and these are the Kähler parameters, the complexified Kähler parameters. So the mirror map relates these two. This is this tau. This is this tau. This map. There's a well-defined map that one can also compute. But so knowing this, the statement is that this is the same as this. So this is something you can do sort of classically and solve some differential equations and try to, and you can obtain this and combine with the mirror map, which is also given by a well-defined algorithmic procedure. You can compute this quantity because this function, this is the same as this once you evaluate it as a function of t, and then you make the expansion its q expansion. Remember, q is e to the minus, q to the beta is e to the minus beta I t. I sum over that, or product over. So you can compute this using this mirror Calabi-Yau, and that was the sort of magic of mirror symmetry, and led to some of the surprising results. So this was sort of the summary of what I said last time, and this used the fact that. So in particular, we were actually, though there is a more general statement, most of the work on mirror symmetry focuses on the case G equal to 0. It's true more generally, but let's say most of the explicitly known results are for G equal to 0, which is where it's much easier to compute even these classical things on this side. It becomes more difficult otherwise. So this is the statement that, remember I motivated T-duality, that string theory sees a circle of radius r and circle of radius 1 over r in the same way. Similarly, string theory sees a Calabi-Yau and its mirror in the same way, which is why you have this equivalence. And that gives you this striking, so it's the complementarity of these descriptions that gives you this striking power. But this is true sort of genus by genus. It's true for each G. And in here I talked about G equal to 0. So you have the genus 0 to the Calabi-Yau, and you can do the statement. Then similarly, you can talk about genus 1 and genus 2 and so on. And this is true genus by genus. So you say this mirror symmetry is a duality of classical string theory. This classical is different from this classical. This is more classical differential geometry. But here, classical string theory refers to sort of the statement that it's true in term by term for each of these world sheets. So for a given world sheet, you have this equivalence, and in particular, the genus 0 is the so-called where there are no pants in this diagram, or rather only the trivial one. So there's no genus, so there's no loops. It's sort of the analog of non-interacting string theory, which is why it's called classical. So it's duality it's a sort of a simpler duality as we go in this ladder, because the next duality I'm going to talk about is something in which is not true term by term for every genus. So here in fact, the natural quantity, I talked about this Fg as the maps from a genus G Riemann surface to from your world sheet to the target space. But the natural quantity that people actually consider in string theory is a generating function in which you sum over all the genus. And this G little s, well, this is I should maybe use another term. Maybe I'll use lambda. So this gives you some function f of g and lambda, f of t and lambda. This is the so-called full, the total free energy. This was the genus G free energy, but this is the full quantity. You have a generating function. Lambda, just think of lambda as a formal parameter for this expansion, and power series expansion. So this is in some ways the natural thing to consider, because this genus expansion is just a kind of expansion in powers of these loops. The genus is sort of reflecting the strength of the interactions, because you can see that the more genus you have, the more pair of pants you need, so the more vertices you need in the interaction. The string vertices were the basic pair of pants. So here you have more pairs of pants than over here. So this is an expansion, and this is called the string coupling, because it tells you it's a measure of the strength of the interactions. So with every genus, you sort of, if you give a weight, that the interactions are suppressed by some factor of lambda square, the relative suppression between one genus to the next. Then this expansion is what you normally write down as a so-called perturbative expansion of string theory. So this is what you call a perturbative expansion. From a physics point of view, you can think of lambda as playing the role of Planck's constant, h bar, because that's what, roughly speaking, each loop gives you an extra factor of Planck's constant. This is similar to the perturbative expansion, Feynman diagram expansion in field theories, but this is the perturbative expansion in string theory. And the earlier statement was that we have the surprising equivalence for each term in this expansion, each of these FGs. But what one learned in string theory in the mid-90s to 2000, and so on, that string theory has even more surprising equivalences, which are not visible sort of when you do a term-by-term expansion like this, genus-by-genus expansion. There are further dualities or equivalences, which are, so to say, strong, weak dualities. So strong and weak refer here to this coupling lambda. So typically, very roughly, there's equivalences which relate a theory with small value of lambda to another with a very large value. So just like we had the T-duality, which basically said that string theory on a circle of radius r is equivalent to that of radius 1 over r. This is an equivalence between theories which have coupling lambda and 1 over lambda. So if lambda so in other words, a theory with a small coupling is equivalent to a theory with a very large coupling. If you think of lambda as dimensionless number between 0 and 1, then roughly there's an identification between the regime 0 to 1 and the regime 1 to infinity, that there's an equivalence. Sometimes these are more sophisticated. There's a whole SL to Z family of equivalences and so on, but I won't talk about that. But this is the simplest kind of, so it's a strong, weak equivalences. So there are, I'm just giving you, again, a very crude flavor of things. Very often, just like in the Calabi-Yau, you have to go to a mirror, you have to go to maybe sometimes a different string theory, string theory defined in a slightly different way. There are a few different categories of string theories. The difference is sort of largely technical. So it may relate strong coupling of one to weak coupling of the other, and vice versa. But there's a general strong, weak equivalence of theories, which is not something you would see term by term, right? Because if I focused on any given term, there you would not see such an equivalence, because this is just a series expansion in lambda, and by taking lambda to 1 over lambda, that scrambles up this whole expansion. So it's so this is something you would see, in a sense, only in the full object, the full generating function, and not in any individual term in the generating function. It's like a modular form or something like that. Each individual term in the modular form expansion is not invariant under SL to Z, but the whole sum has an invariance under SL to Z, or tau goes to minus 1 over tau. So in a way, very often, some of these objects, especially in terms of some appropriate complexified coupling, have properties like that of modular forms. So they have, in fact, not just a Z2 invariance, but something like a SL2Z invariance. And this lambda is often like the imaginary part of a complex parameter, tau, the modular parameter, and the equivalences are things that you have for this. So the strong weak equivalent is the statement that something like this, the analog of this, would be modular, would be a modular invariant form. So there are these, people discovered these equivalences and these strong weak dualities. So so you can ask, this is true in the full physical string theory, and you can try to ask what reflection of this is there in the topological string theory, which had which has this mathematical interpretation. Like I said yesterday, the physical string theory perhaps is less of interest to the mathematically, or it has sort of a lot of extra stuff in it. But the topological string theory sort of captures some very basic mathematical quantities. And there, the mirror symmetry led to this sort of very surprising equivalence and new results. What do these kind of strong weak equivalences lead to? Well, one of the things they lead to is that if you maybe if I'll write it down, is that there's a natural way. So the question is, what do such equivalences imply for the topological strings? And therefore for enumerative invariants. So one of the things one can one finds is that for the A model, for the topological A model, the on a Calabi-Yau threefold. So on a Calabi-Yau manifold M, the f of this d lambda has the following structure. So I'll write it down, and then I'll try to explain what it means. So one concludes that it has a structure which is not evident from, which will not be evident from this way of writing. As you will see, it is it will be written differently. The sum over beta is the same sum as before, but then there's a sum So I claim that the dualities tell you that this this object in which, so this is, you could have written this as equal to lambda to the 2g minus 2 q to the beta n g beta sum over g equal to 0, sum over beta. Okay. Let me write from this. Q to the betas. So this was what, this is just the definition here, the formal power series. And these were these Gromov-Witten invariants. Right? This is what you heard probably talks about. But I claim the same thing here can be rewritten in this way, which is a different way of reorganizing the sum. So there's now the lambda dependence here was just some power series dependence, but here it comes in a more complicated form. And there's some extra sum here in terms of some in a positive integer d. There's, of course, a similar sum from g tilde. I wrote g tilde instead of g just so that you don't identify those two. So it has a sort of similar structure to this, but is actually something you would see only if you reorganized this sum. You talked about the whole sum. It's not something you would see individually. And moreover, I think the most surprising statement here is that these are integers. And so this is there's a physical reasoning, which is what I will try to just give a flavor of. Comes from these equivalences that I talked about. Yeah, so algebraically, so it's not obvious just given this that you will have a reorganization like this in terms of integers, but I think this has recently been proven by probably Ionel and Parker I think the paper was published in Annals of Mathematics just this year sometime. It was probably announced a couple of years ago. So at least for a class of Calabi-Yau, and a part of this, I think they have shown that this is true. So the statement is that these things are integers. So where does such a statement come from, and this sort of reorganization? So it comes from the fact that there are two ways to view this. Like I said, it's more natural if you're considering such strong weak equivalences to talk about this whole thing, not the individual terms. And this whole thing, if you think in terms of some equivalent theory, so this was the topological A model on a Calabi-Yau. This is a part of a physical string theory. As I said earlier, this topological strings are a sort of a subsector of the physical string theory. So for that physical string theory, it is a so-called type 2A string theory on this Calabi-Yau, and there is a strong weak coupling equivalence in terms of another description, so-called M theory description, in which the contribution to this partition function would come from the contribution to this F would come not from world sheets like this, but from completely different objects called D-branes, which are sort of the D's for Dirichlet. These are sort of higher. They are not. They are like membranes and so on. So the brain is coming from the word membrane. So these are objects in string theory that are, so to say, non-perturbative objects, or solitons, if you're familiar with that kind of term from quantum field theories. They are solitonic objects, and so the D-branes are the D-branes contribute to f this function at strong coupling, meaning you can view the contribution you can view the calculation of this f of t lambda as coming purely from a different class of objects called D-branes, which are these solitonic objects which can wrap on cycles inside the Calabi-Yau and give contributions to this free energy, and their contributions can be explicitly evaluated. And this is roughly the contribution, well, this whole thing is the contribution of a single D-brane wrapping the cycle beta. These are integers because they essentially count the dimension of a Hilbert space of the states of these D-branes. So the ng beta, or the ng tilde beta, are, roughly speaking, the number of D-branes actually D2 branes on 2-cycle beta, because remember beta was part of H2, so D-branes wrapped on these 2 cycles. This 2-cycle beta and D2 which with topology with genus G tilde. So this roughly speaking, I mean, this is a very rough, it is not a very precise statement. There are some, you have to say it much more precisely, but they are, roughly speaking, they are more accurately a so-called index, or some number of BPS states. So-called index of so it's a dimension of a particular Hilbert space, but these can be positive or negative, so it's that's why it's an index. So there's a sign also. It's a signed trace over a Hilbert space, a graded Hilbert space, so that's why these are integers. So that's the physical intuition for why you can rewrite it in this way. So the strong coupling picture of the same system tells you that you should think in this language, and then this is the contribution from these branes, and this is basically the integer number of such branes. So this is a way of rewriting it, which is suggested by the physics, and it's not something that would have been perhaps obvious at all from any mathematical point of view, that you could or should reorganize things in this way. But there's a way to maybe give some physical picture of why these combinations on maybe what these combinations really mean. So to do that, you can now try to re-expand this in this terms. At least you can try to re-expand it in powers of lambda, because this you can do an expansion of this in powers of lambda and try to say try to express the fg in terms of these integers. So by the way, these are always typically some fractional numbers for most Calabi-Yaos. So it's surprising that these are integers. But if you try to expand this expression, so expanding in a power series in lambda, one finds, and that's just a matter of some algebra, one finds that the fg of t can be written in the following way. I probably need more space. There's an expansion you can make, which is of this form. So what I'm just doing is expanding in a power series in lambda, and one finds for the coefficient of lambda to the 2g minus 2, which is what this fg of t is. So if you want to read off fg of t, you just expand this in powers of lambda and collect the coefficient of lambda to the 2g minus 2. And what you find is that if I look for a fixed g, it actually gets contributions only from a finite number of g tildes. Because you see, if I fix a g equal to 20, the g tildes for g tilde greater than 20 will not contribute, because sign to that power will start with power, the expansion, power series expansion in lambda will start with a higher power. So the only contributions to a fixed g, to a fixed power of g here, will come from terms with g tilde less than g, and those are the terms I've written over here. So there's the term with g tilde equal to g, with g tilde equal to g minus 1, and all the way 2 and 0. So there's only a finite sum, but then there's these q's to the d beta, and there's the sum over d, which actually, when you work it out, you see that it just becomes a polylogarithm. So this Li is a polylogarithm. Let me remind you, Li k of x is just summation. It's just the generalization of the polylog to x to the n by k to the n. Essentially something like that. Is this visible? Yeah, I don't want you to necessarily this thing take all the numbers here. I mean, there are a couple of points here that I just want to just make. Firstly, that this is a finite expansion. I mean, this term in brackets is just a finite thing from genus G to from G tilde equal to G to 0. So there are a finite number of integers which determine the genus G contribution. There's just a finite number of integers that determine the genus G contribution, which are basically these, all the way till here. So this is the non-trivial statement that this original expansion here can be recast in this way in terms of integers. So it's not surprising that when you sum these all up, you'll get some rational numbers, because all the terms that appear here are rational. By the way, this is the Bernoulli number, B to G. So these are rational numbers. These polylogarithms also give you some rational pieces. So you get some rational numbers, and the statement is that all those rational numbers, if you decode them, they're actually expressible in terms of a specific set of integers. These are not any arbitrary integers. There's just as many integers as labeled by these. So it's the same sort of, instead of rational numbers like these, you can rewrite in terms of integers like these. So let me just try to give what I guess is also probably, the physicist picture of what these terms are roughly like, and how to interpret maybe each of these terms. So first, let me say something about the polylog. Actually, this is not something that is, the polylog dependence is actually not something that is very surprising. Even for genus G equal to 0, I think maybe some of you are aware, people actually knew that there is a poly Li3, if G equal to 0, you get a Li3, which is x to the n by, sorry, this should have been n to the k. X to the n, yeah, n to the k. So you get an n cubed kind of dependence, and these are what are called the multi-coverings. So the polylog piece captures multi-covering of the sigma G to, the maps, the multi-covering maps. Multi-covering maps are the ones in which you can, supposing you have a holomorphic map from your genus G targets, genus G worldsheet to, let's say, some cycle in your target space, you can compose that further with another map, which is of just degree D, which just wraps multiple times on the same cycle. And this, in a way, is a kind of a trivial contribution. So when we have terms of sort of D times beta, very often those are, there's a primitive map to the cycle beta, and then there is another trivial map which sort of just multi-covers the beta to D times beta, multi-covers it D times. So this sum over D is really to be interpreted as a sort of a multi-covering. And this part, I think mathematicians are even for the case at least G equal to 0, and later for arbitrary G, one can show that the multi-covering contributions, so this is the piece which is sort of a multi-covering contribution, and that's relatively trivial. It is not, I think, such a deep statement. There are so you factor that out, but then there's this sort of finite sum, and again the rough interpretation of this is something I think which at least physicists call bubbling, but I don't know whether that is standard maths terminology. So bubbling is the statement that you can have degenerate maps. Supposing you have some genus G worldsheet, and you map it in the following way to, so in the target space, let's say you have a smaller genus surface, let's say a genus 1 surface, let me draw this first. And then I draw sort of it's essentially a degenerate map in which basically most of the Riemann surface here, this part is sort of mapped to here, and this part, the extra handle, is mapped to a point. So you can have a sort of a degenerate map in a sense, it's on the sort of boundary of the space of holomorphic maps in which there's a non-trivial piece which wraps, but then there's another piece which is sort of shrunk to a point. So this, you can see, it could happen. You could have degenerate maps like these as well. So genus 2. So the whole thing, so it's only, let's say, this part is mapped onto a sphere, but the rest of it is pinched to a point. So it's like most of this Riemann surface is it's an almost constant map, but there's some part of it which is sort of wrapped. The D-branes are also wrapping these surfaces. So the D-branes are the things that were giving these contributions. And that automatically takes into account these multi-coverings. So the same D sum reorganizes itself in this way. No, so the D-brane is actually wrapping here. So here you can have a D-brane wrapped multiple times also. And that's where, so if I have one D-brane wrapping it, I can have n D-branes also wrapping it, but with a multi-covering. So those are what this is contributing to, which is sort of like the contribution of a Riemann surface, which is mapped, then you compose it with a degree D. So a multi-covering comes from composing a map, a primitive map, and then another map which is sort of a degree D from M to M itself. So it's sort of like a composition of these two. In a way, the D-brane picture is capturing that aspect of it, this part. And it gives you this kind of trilogarithm, polylogarithm. But it also captures the fact that, so these can be viewed as contributions from wrapped D-branes in which paths have been, in which, so these can be viewed as contributions from degenerate maps, in which a part has been pinched off. And that's why you see I can have honest maps in which genus G surface gets wrapped to a genus G surface. That's actually counted by this. But then I can have contributions also where a genus G surface is mapped to a genus G minus 1 surface, which is sort of what this is, the D. So that's captured when the D-branes wrap here with, so the G tilde, which is G minus 1, or similarly G minus 2, and so on, all the way to genus 0. So here I've just drawn the case where G equal to 2 here. So you have genus 2, genus 1, and genus 0. So in a way, these contributions are sort of these sort of bubbling. They're called bubbling because I think in a sense you kind of have that Riemann surface has developed some sort of a bubble of this kind. So these pieces are what at least physicists call bubbling geometries. So one has a way of sort of at least giving a picture of what these different contributions are. Yeah, so that's what this formula tells you. This kind of decomposition has now been checked multiple times, I think, and as I said, in some cases, it has also been proven. There's also an element of this which is a certain finiteness, which is that these integers are 0 for g greater than some g tilde. I mean, for these integers vanish for any given beta. There's a maximal g tilde, which is the statement that there's a maximum sort of a genus surface, maximum genus in that homology class, so you have certain finiteness property and this kind of an expansion. So yeah, so this is, I think, the interesting feature of these of this reorganization, and it kind of gives you what are, in a way, the more fundamental integers as opposed to the original Gromov-Witten invariants. But I think a full mathematical definition of what these integers are, in a way, I think, just like these were defined as some integrals, some Euler characteristics of the moduli space of stable maps of genus G, and so on. I think I mean, people, I think, are still developing a mathematical theory which will help to define what these integers are. Yeah, that's outside my expertise. So that's so I just told you about what these kind of dualities also tell you, make some surprising statements about these enumerative invariants. So finally, I should talk about this last class of dualities, which perhaps give the most surprising kind of a statement of all, but which I think has not been mathematically even unraveled or framed, defined in any satisfactory way, as far as I'm aware. At least over here, one can potentially try to define these quantities, and at least people have proved that there is an integer expansion of this kind, even if these numbers have not been defined from first principles yet. So let me start on this last part. But any questions before that? Yeah. Yeah, it's not completely obvious to me because some of the strong weak coupling dualities are very specific to Calabi-Yau threefolds. There may be some variant which you can try to find. I don't know if anyone has explored those cases. Maybe the Calabi-Yau twofold, which is basically K3, there might be something, but there I think there will surely be something, but higher dimensions, I don't know. But maybe this suggests, I mean, many aspects of this don't seem to be so much tied to Calabi-Yau, so perhaps there is a reorganization that way. I mean, once one has this formula, one can try to see whether it makes sense to organize other things this way. So far I talked about a perturbative expansion, but this is in actually, to be more precise, what is called closed string theory, because these are all Riemann surfaces without boundaries, and that's what appears when you talk about propagation of closed strings. You can have punctures, which are sort of closed strings coming from infinity and going out to infinity. If you can formally map them, they become punctures. And so typically, a closed string expansion is an expansion in Riemann surfaces of genus G and maybe some n punctures. If you want to put, I didn't, for this FG, I didn't put in any punctures or marked points, but you could. But there is something called an open string theory as well, in which you consider open strings. Open strings are objects which have endpoints, like if a closed string is like a rubber band, this is just like a piece of thread with two ends. And when these trace out history in time, they trace out a Riemann surface with boundaries. So typically, in a theory, you can have a theory of purely closed strings. In a sense, there are some theories of purely closed strings, but often you have both open and closed strings, because two open strings can combine. Two open strings can combine. You can imagine that these can combine to form a closed string. The endpoints sort of meet, and you can draw a picture of how that happens. Two of these come and meet and glue and form a sort of a cylinder of a closed string. So you can have, so in open strings, when you have open strings, you have a perturbative expansion in open and closed strings this thing has Riemann surfaces with boundaries. So with disks cut out of them, you can think of these disks as corresponding to an open string, which is it's a boundary corresponding to an endpoint of an open string, and you can make pair of bands decompositions of these general Riemann surfaces. So you have perturbative expansions in open and closed strings as well. And in fact, people have recent years, talked about similar things, but now for open and closed strings on Calabi-Yau, and people have talked about the topological sigma model. You have an analog of mirror symmetry for open and closed strings, and these are the so-called open Gromov-Witten invariants. Maybe they are called in maths that as well. There's a generalization now when you have genus G, but also maybe some K boundaries. So let me not spoil this equation, but you can have some number of some genus G, sigma G, and then K, and then maybe some marked points as well. There'll probably be two kinds of marked points on the boundary, marked points on the interior. And so there'll be a more general expansion of these objects. And so you can define the free energy FGK, which is just similar to above, except now you have genus G and K. I'll, as before, suppress all the marked points and just talk about the number of boundaries and the genus. So you can define these, and there's sort of an open Gromov-Witten invariant expression like this, which, yeah. So that those are also sort of, I think this is also gives you a certain class of interesting enumerative geometry questions, writing out the analogs of these. And you have you have an analog of mirror symmetry for these objects as well. So I won't talk about that, but you can do something similar for them, and you can do something similar for these as well. You can write down similar expansion for these, but these gauge string dualities now, so what are they? That corresponds to yet another very unsuspected, previously unsuspected relation or equivalence in string theories, one more further in the ladder, which, so I should say one thing, that I mentioned this in passing yesterday, that closed string theories of this kind are the things which generalize Einstein's gravity, which contain Einstein's gravity but go beyond it. The theories with open and closed strings, they contain Yang-Mills theory as well as gravity. The open strings can be viewed in some ways as sort of the lowest excitation of an open string is actually can be viewed as a Yang-Mills gauge field, or a vector field, as it's called. Whereas the lowest excitation of a closed string gives rise to gravitational excitation, or a graviton, or the underlying quantum of gravity. So roughly speaking, open strings are more closer to gauge theories, and closed strings are closer to Einstein gravity, generalizations in a sense. So the surprising statement, that's why sometimes it's, what I'll talk about is sometimes called a gauge string duality, because of the following reason. There seems to be an equivalence between open string theory and open closed string theory, at least in the limit where it is a gauge theory. And a pure closed string theory. On a different space-time typically. So let's say open-closed theory on some M, and another M prime. So I like to draw this as the following cartoon, that if I consider, let me draw the diagram. This is my sort of a Mickey Mouse diagram. Or Cheshire Cat diagram. So this is basically supposed to illustrate that there appears to be a rather remarkable equivalence in which you consider this side the open-closed string theory, open-closed strings, or which is sort of most cases a sort of a gauge theory. You usually consider it in the limit where it reduces to a gauge theory. So this statement is the statement that you sum over all the, so K. So you fix, this is fixed G. So for any fixed genus, you have diagrams with arbitrary number of boundaries. You sum over the contributions of all of those, and the claim is that you get a closed string theory, a theory without any without any boundaries in it. So this is a statement at the level of the world sheet, and you get a theory purely of closed strings, but in a different background M prime. So to write it more, maybe more in equations, I defined these F, G, K, let's say of and let me weight it like this. So this is the left-hand side, where I have these quantities with genus G and K number of boundaries. And I weight it with, take a generating function again. And I have the same kind of lambda, string coupling. And the statement is that this is equal to some Fg wait, let me just write it like this. So the claim is that this is a little misleading because let me put this here. Dependence on lambda in the, so if I put lambda So what I get is one of those closed string amplitudes, the Fg of t that we been talking about, but on a different space-time, a different background, as it is called, a different target space, which is labeled by lambda. I mean, there's a parameter lambda. It could be the size of that space-time, and so on. This gets converted to something like that, so this is the rather surprising fact that sort of the closed string, the open string theory on some space-time M, if you sort of sum over all the holes, the boundaries, you get a closed string description on a different space-time. So this is a different kind of dualities from all the ones that I have said so far. It's another kind of an equivalence. And this, at least, so this is believed to be true in a large. So this is the thing that has been driving a lot of work in string theory in the last 2 decades, in a sense, to sort of delineate the class theories for which such dualities hold. And these are, it's not known in what level of generality this holds, but by now there are many, many examples, and it's believed to be a very general phenomenon, and that's why so this is why work continues on this. And it is a very deep statement because it relates to very different things. So as I said, this is more like a gauge theory, and this is purely a closed string theory. In many cases can be reduced to a gravitational theory. Some limits, it becomes just Einstein's theory with some corrections from string theory. So it relates gauge theories with gravity in a very non-trivial and unexpected ways. Both of these are structures that have predated string theory by almost a century. I mean, the mathematical and physical theory of gauge fields and their properties is well-studied theory. Similarly, Einstein's theory and even its corrections from string theory have been very well studied. But the statement is that there's a very novel equivalence between these two. And in fact, this equivalence is sometimes what is called a holographic equivalence, but I won't get into that. Physically, it's very, very tantalizing, very remarkable duality. It is, as the Americans say, a gift that keeps giving. We have been learning more and more about it, and a lot of remarkable physics has come out of this general equivalence, which was first proposed by Juan Maldacena in the context of a particular gauge theory and a particular string theory in the so-called anti-de Sitter spacetime. But if you try to see what might be the consequence in the context of these topological string theories, you come across, again, a very striking statement, just sort of stated very briefly that basically so I'll ask the same question as I asked over here. What does this imply for the topological string? In fact, I sort of wrote this equation as sort of for the topological string, if it were to hold. And so it, as I said, implies a very remarkable fact To explain that fact, I have to again quote one fact for you, which is that due to Witten, before all these developments, around the time when he defined topological strings around early 90, that Witten realized that this open-closed, or whatever, this topological string A model on the cotangent space of some three-dimensional, now let me not use M, I don't know, T star N, let's say, is equivalent to Chern-Simons theory on N. So N is a real three manifold. For instance, it could be S3, for example. And T star N is just the cotangent space of N. It's a six-dimensional manifold, and it's, at least in the case of S3 and a large class of three manifolds, this is a so-called Lagrangian. So this is like the phase space associated to the original space N, and it can be given a Calabi-Yau metric. So T star S3, for instance, will be the case I will just mention. So N equal to S3 will be the case, but I'll talk about. But some of this is more general. So this side, which is a gauge theory, in this case is a much simpler gauge theory, the so-called Chern-Simons theory, for which Witten received his Fields Medal, which computes topological invariants of three manifolds, these N's. So Chern-Simons theory on N, and gives you, if you define appropriate quantities in that, the so-called Wilson loops, they give you knot invariants on N and so on. So what Witten realized was this interesting connection between the open string theory and Chern-Simons theory. This is not, I must stress, this is not a duality. It is just a sort of a by definition statement that, in a sense, what does the topological string A model compute? It's basically computing what the Chern-Simons theory does. So that's not a non-trivial statement or anything. It's what the theory is. The non-trivial statement is this connection. So I'll just conclude by just saying what it tells you in the simplest case. But it has now been generalized to a larger class. So in the case of S3, the T star S3 is what is called deformed conifold geometry. This is what you can give a Calabi-Yau metric on it. You can think of this as the geometry in C4 with this relation where mu is a parameter, complex parameter. So this is an equation in C4, x, y, z, w, and this is just a complex parameter. It's called a deformed conifold geometry because the geometry of this T star S3 can be viewed as a cone over S3, an infinite cone. So you can think of S3 and there's a cone from it. So a cone whose sort of cross section is S2 times S3. This is the geometry of this T star S3. So the statement is that topological string theory is on this. So the statement I just made here is that the open-closed a model on this space, this T star S3 or the S3 deform conifold, is the same as the Chern-Simons theory on the three-sphere, the Chern-Simons quantum field theory defined on the three-sphere. No, it's just a quantum field theory with the Chern-Simons action. It just has a gauge field. So I should have said something. There's a gauge field with rank, let's say rank k. When you talk about this, you have to also specify an additional. Well, I've used k. I should use some other letter. Anyway, there's a Chern-Simons theory with a vector bundle, the Chern-Simons connection on with a group, let's say SU or UK. So it's purely a quantum field theory. This is the field theory that Witten defined and solved and could compute many things with. So this is something that is just a particular example of this, and this is the geometry corresponding to it. So what does this equivalence say in this particular case? It actually says that this is equal to the closed topological string A model on what is called the S2 resolved conifold, which is in a way in some sense some kind of a dual of this in the following sense. It's also a cone over S2 times S3, but except that there's no conical at the conical point. You've sort of deformed an S2, so this is what is sometimes called O-1 times O-1 bundle over P1, and that's what gives you a Calabi-Yau, and you can describe it in different ways, but basically this is the geometry. So the statement is that the non-trivial statement of this duality for this particular case is that if I compute the Chern-Simons theory on S3 through quantities like this is what the Chern-Simons, this is what the open string side is, that's equivalent to computing the enumerative invariants on this other conifold geometry, these closed invariants, which are just measuring these wrapped curves, and you can actually, in the case of S3, explicitly check this because Witten told us how to solve this theory, and you can explicitly write down this left-hand side for any G. You can compute this sum. You can compute this whole left-hand side, and you can, at the same time, this geometry is also simple enough. In fact, using this kind of way of writing it, one can actually read off this fg of t for the conifold. So this is what I was calling m prime of lambda. In fact, lambda becomes the size of this S2. So this was, in this language, the m, and this is the m prime. So you can compute this independently for the conifold. It is just counting. In fact, it's a very trivial case in which this S2 resolved conifold is the one in which there's only one non-trivial cycle beta, which is this S2, because this is actually a non-compact Calabi-Yau. This is an infinite cone. There's one non-trivial cycle, this S2. and of genus 0. So this is an integer, just one integer, n0 beta, which is equal to 1, and that's it. So all the rest are, so it's only this which is non-zero, and all the rest higher genus are 0. So you can actually write down this explicitly. So you can compute this explicitly, you can compute this explicitly. They refer to two very different mathematical objects. This refers to knot invariance and topological properties of real three manifolds, whereas this refers to some complex holomorphic curves, Gromov-Witten invariance on a different topologically, this manifold is topologically distinct from this, and this. So this is a very, I think, quite unexpected equivalence between two. Now it's an equivalence between enumerative geometry questions and topological questions about three manifolds. And it's not, this is not just an isolated example for which otherwise it would have been a curiosity, but this is true more generally. And for many, you can do this also for the knot invariance, and you can find a way of translating knot invariance into questions about enumerative geometry. So knot invariance in 3 dimensions are related to questions of enumerative geometry in this Calabi-Yau, which is of 6 real dimensions. And moreover, we know, as I described over here, that the FG of T have various non-trivial, has a non-trivial structure like this with many integers. So if you actually translate that, you get some surprising statements about knot invariance, that there are integers hidden behind the knot invariance, which are actually, again, not very obvious to see, but which, again, you can check and find, verify, and so on. But there's no still theory which allows you to understand. There's no mathematical understanding of what this connection means, why things about knot invariance in 3 dimensions, or more generally, these so-called Reshetikhin-derived invariants, which is what these quantities, the free energy or partition function gives you, what these have to do with enumerative geometry and invariants like these. So that's, I think, a reflection of how physics, the dualities of physics, tell you quite, make clearly what seem to be true statements, because at least they have been verified in highly non-trivial ways in a variety of examples. So they appear to be true. So they enable physicists to conjecture that there are some remarkable equivalences which come from the underlying equivalences of string theory. Yeah, so at least at least string theory is the source of quite novel and unexpected sort of conjectures or relations. So I'll stop over there. Thanks.
Questions for the speaker?
Yes. Yes.
You would, so in your simplest case, the boundary condition was the S3.
Yes.
Right?
Yes.
So what does physics predict in general? What type of boundary conditions do appear from
Dirichlet boundary conditions, well, in the language of the string.
Or is it,
sorry?
Is it always spheres, or is it other?
So in this class of quantities, the statement is that the boundary of the boundaries get mapped to these to the zero set. Yes.
But so is it just cotangent bundles, or are there other
so you can then try to put together many of these, and so I think the most general class of this has not been the most general class in which this holds has not been sort of charted out. People have gone beyond many of these cotangent space things. There are, of course, lens spaces and other things that people have done. But then there's a whole other class of toric Calabi-Yaos, for which also people have verified that this holds. But I think So I think the most general case is still not known.
And equivalence with the TS TQ.
Yeah. That's a particular case of this Witten's equivalence, yeah.
Is it predicted that it is true on general compact closed-oriented three manifolds?
This one? I think they probably have to be... so you need to be able to satisfy you have to be able to put a Calabi-Yau metric on them at least. So what restrictions that places on n, I can't, probably it's known, but I can't say it offhand. It may not be true, for instance, for T3. I think it's not true for T3, if I'm not mistaken. There's a flat metric, yeah, but yeah, so it's probably a little trivial in that case, but yeah, maybe it's sort of trivially true or understood. You can understand it as some degeneration or something like that, but yeah.
I have kind of a vague question. When you hear the following phrase, physicists or physics predicts this deep fact about something in mathematics, and then mathematics takes like another 10 years to possibly try to catch up. What does that mean?
What does that mean?
Yeah. What does it mean for physicists to be able to predict that? I mean, this is not a well-formulated...
Well, physicists suggest that there are such equivalences, and physicists prove it or understand it using their own I mean, the physicist's notion of proof is perhaps not mathematically rigorous, but in many cases, actually, in some of these things, there's not even a physicist's proof of these things. There's a physicists have also conjectured many of these gate string thing is still a conjecture, even from a physics point of view. I think even a physicist wouldn't say that they have a proof of it. But in some of the things that I think in mirror symmetry, for instance, there's at least a physicist's proof. Physicists can sort of don't think, they wouldn't call it a conjecture that there is a mirror Calabi-Yau, because they can sort of see using this thing that there is these are more conjectural even from a physics point of view. And so physicists convince themselves of the truth, at least the provisional truth of these statements through many examples and computations. And so it's a sort of a very low-level way of, but empirically kind of confirming it, experimentally confirming it. And then you see fairly I mean, most of these things, for them to work, require at least apparent miracles to happen. And the fact that they do happen convinces people that they are true. But of course, being true is not the same as proving it or even understanding it in a deeper way. Yeah. So I wouldn't say for many of these, even physicists they believe these statements. They believe because they feel they they're too good not to be true. But they wouldn't even, I don't think even physicists would say they completely understand, for instance, these gate string dualities. Even from a physics point of view, a deeper, there are levels of understanding, and one has reached a certain level of understanding. We wouldn't say that it is complete even there. But yeah, that's how it is.
Question on a lighter note. Are there examples of physicist proofs which are not mathematically proved?
Yeah, I mean, physicists always have, even Chern-Simons theory, well, I mean, what Witten computed was something that everyone would accept as a physicist. Any physicist would accept that as a proof for a derivation. But I think mathematically, probably now, for some of the cases, you can argue that maybe more rigorously, but typically physicists use these techniques called functional integrals, and they have or path integrals, which they have a rough and ready way of dealing with them, even though they are maybe not mathematically well defined because they involve integration over function spaces, infinite dimensional things. But there's a heuristics of dealing with them, which people have always landed on their feet doing that. And often been experimentally verified by nature. So given that, people, physicists would say, yeah, Chern-Simons theory on the three-sphere, we know how to compute it. And maybe in that case, perhaps mathematically now, there are the same, but I think when physicists proved it, I don't think mathematicians would have accepted that as a proof. But yeah, like I said, mirror symmetry also is something physicists think they have a proof, but I don't. Maybe now for a large class of them, mathematicians have a proof as well, but.